All right, last lesson of the week, last lesson of the chapter, last lesson of the unit, and it's my favorite. When my mom assigned me the student teaching project when I was in her pre-calculus class, this was the lesson that I taught. So I taught it at 16. Hopefully I can still teach it now. Here's your learning objective: perform partial fraction decomposition, which sounds crazy, and it is, but it's really fun. And then here's your homework. That's not going to be due until next Friday. Okay, let's get started. How do we combine fractions? We get common denominators. Okay, you remember this. We have this fraction and we have this fraction, and they need to have a common denominator, so you multiply whatever you're missing from one fraction, you multiply whatever you're missing from the other fraction, blah, 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 so you can combine your like terms and get together one fraction. But can you do it backward? Can you actually be given a fraction and then change it up into separate fractions? I don't know. That's what we're going to do today. So let R be the rational function. R of x is equal to P of x over Q of x, where the degree of P must be less than the degree of Q. Okay, there's this theorem in previous chapters, and we kind of brushed over it last term in Algebra 2 Trig, but it's kind of, it makes sense logically. Every polynomial with real coefficients can be factored into a product of linear and irreducible quadratic factors with real coefficients. So if we don't use complex numbers, then a polynomial with real coefficients can always be factored into linear and quadratic factors. A quadratic polynomial with no real zeros is called irreducible over the real numbers, meaning its zeros are complex, not real. So you can't factor unless you factor using imaginary. Okay. For example, if we had this as our denominator, as our q of x, if x to the fourth minus 1 was q of x, then we would need to factor it completely. And you can see that its irreducible factors are here. You have a linear factor, and an irreducible quadratic factor. Irreducible factors come in the form of linear or quadratic, and A, B, C must be a member of the set of real numbers. So, back to what we were saying before, let R be the rational function. R of x is equal to P of x over Q of x. Once you've completely factored Q of x, you can express R of x as the sum of partial fractions. This is called partial fraction decomposition. Dun 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 dun. Okay, so let's do it. Case 1. Denominator is a product of distinct linear factors. Okay, so you factored out Q of x. It's all linear factors, and the partial fraction decomposition takes the form A sub A1 over A1x, A sub 1x plus B sub 1. Then you have the constant A sub 2 over your second linear factor, and so on until you get the final linear factor. Okay, A sub 1, A sub 2, and A sub n are all constants, and I'm going to show you how to find those pretty soon. Okay, so we're going to first find the partial fraction decomposition of the following. Our first step is to completely factor our denominator. So Q of x is equal to this polynomial. I'm going to factor by grouping. So from these first two, I can take out an x squared. X squared times x plus 2. And from these two, I'm going to take out a negative 1. So that I'm left with positive x, positive 2. Okay. In each of these pieces, x plus 2 is a factor, so x plus 2 times x squared minus 1. Okay, we can actually factor x squared minus 1 one more time. We get x plus 1, x minus 1 as our difference of perfect squares. Okay, that's how we factor our denominator. Okay, so our decomposition takes the form a over our first factor, and it doesn't matter which order you put these factors in, honestly. It's just I did them in a certain order in my notes and I want to follow along with that. So I'm going to put a over x minus 1 plus b over our second factor, or whichever factor you want, plus c over our final factor, x plus 2. This is the form that this fraction is going to take when we split it up. So now we have this giant equation, and we're actually going to be able to solve it. First, we're going to multiply both sides by our denominator over here, which is x cubed plus 2x squared minus x minus 2. I'm going to write its factored form. So we have x plus 2, x plus 1, x minus 1. And then you're multiplying both sides of the equation by that. Okay, go ahead and multiply. Notice that you'll have no more fractions after this. So you have 5x, you have 5x plus 7 is equal to a times whatever was not in this denominator. So x minus 1 is the denominator of a, so the other two binomials, a will be multiplied by x plus 2, x plus 1, and so on. Kind of ran out of room for a second with c. Okay, now we're going to continue to simplify, so multiply these binomials. This next step I'm going to show you here, but I'm not going to show you in the next examples, so look out for it. We're going to actually distribute in the a, but we're going to kind of do that in our heads in the next example. So distribute your constants a, b, and c. Now that I've distributed, I'm going to group the x squareds, group the x's, and group the constants. Anything that does not have a variable on it, so that I can get it into descending order. Okay, now that we have these grouped, let's go ahead and factor out the x squared and factor out the x. So I wrote the a, b, c in front of the x squared because a and plus b plus c, these are all numbers, just constants, okay? So I wrote them in front. If two polynomials are equal, then their coefficients are equal. Okay, so this polynomial 5x plus 7 is equal to this one that has an x squared, an x, and a constant. So I'm going to rewrite 5x plus 7 with an x squared term. That would be just 0x squared. Just so it looks like the other side. You do not have to do this. I just want to show it visually. And I'm not going to change the other side, so here it is. Okay. If two polynomials are equal, then their coefficients are equal. That means that a plus b plus c is equal to 0. That means that 3a plus b times x is equal to the 5, because that's what's being multiplied by x. And that means that these constants are equal to this constant. Now you have a system of equations that you can pretty easily solve. Okay, I'm just going to keep it as equations, but I'm going to do kind of row operations or equation operations. Just do it like elimination, put it into triangular form. Okay, so to put it into triangular form, I'm going to take negative 3 row 1 or equation 1 plus equation 2, and negative 2 row 1 plus equation 3 or row 3. which looks like this, and then I'm going to do my last operation, which is -2 equation 2 plus equation 3 to get it into triangular form. Through back substitution, we can find that C is equal to -1, B is equal to -1, and A is equal to 2. So, what is the partial fraction decomposition of this original fraction? Well, remember it's in this form, and now we have A, B, and C. So here we have, okay, and so we had A plus a -1 plus a -1. So you had A, B, and C as the numerators. And here's your partial fraction decomposition. Let's take a look at case 2. Denominator is a product of linear factors, some of which are repeated. So if you have a repeated factor, ax plus b to the k, that means that you have to include everything underneath k. Okay, for example, if you have ax plus b to the power of 3, you have to have a fraction that's over ax plus b to the 1. You have to have a fraction that's over ax plus b to the 2. And then you have to have a fraction that's over ax plus b to the 3. So the form that this one here, example 2, will take is a over our linear factor x plus b over our second factor to the power of 1 plus c over x minus 1 to the power of 2, all the way up to whatever you have here, plus d over x minus 1 to the power of 3. Then we're going to multiply both sides by our denominator, q of x times x minus 1 to the third, x times x minus 1 to the third. Go ahead and pause it and take a moment to do that while I do it too. Now go ahead and pause to take a minute to expand all of this. Alright, let's take a moment to let that sink in, okay, and to check. Now I'm going to show you how we're going to make our equations, how we're going to build our coefficients. So the coefficient for x cubed. Any letter that has an x cubed that is being multiplied by. So a is being multiplied by this x cubed, so you need to have a. And then b is being multiplied by an x cubed, so you need to have b. A plus b times x cubed. Continuing on. X squared. I have a times -3x squared. So that's a -3a times x squared. Then I have b times -2x squared. That's -2b times x squared. And c times 1x squared, that's just 1c times x squared. Okay, the coefficient for the x term. I have a times 3x. That's 3a times x. I have b times 1x. That's 1b. And c times -1x. That's -c. And finally, your constants. You have a times -1, so a -a. You don't have any constants for b, not for c, but for d. Oh no, d was supposed to be in the last one. My bad. D is being multiplied by x, so we're going to say plus d. That's being multiplied by x. And we only have one constant. It's the a minus a. We're going to go ahead and line up our coefficients. So the coefficient for x cubed on the left side, right here is 0x cubed, and the coefficient for the x term is also 0, just to remind you. So you have a plus b is equal to 0. Oh, I did not leave room for the other letters in my system. Next I have this is equal to the coefficient for x squared, which is 1. So you have negative 3a minus 2b plus c equals 1. Coefficient for the x, that's 3a plus b minus c plus d equals 0. And finally, your constant equals your constant. Negative a is equal to 1. Yay, we actually get a through back substitution. We don't have to do any row operations here. A is negative 1, and continue to back substitute. So your partial fraction composition, because c is equal to 0, then this fraction would just not exist, and your final answer is this. There you go. Case 3. Denominator has irreducible quadratic factors. None are repeated. Then you're going to have a quadratic factor in your denominator of one of your partial fractions or multiple partial fractions. So let's do this one. First of all, we're going to factor out q of x. So x cubed plus 4x is our denominator, which I'm calling q of x. Factor out the x squared plus 4. Well, x squared plus 4 does not factor unless you use imaginary numbers. So that would be called an irreducible quadratic factor, x squared plus 4. So your partial fraction decomposition will look like this. A over the first factor plus bx plus c over our quadratic factor. Make sure you have the numerator is linear whenever you have an irreducible quadratic factor in your denominator. Okay, we're going to multiply both sides by, and I'm going to distribute that. Okay, let's go ahead and line up our coefficients to create our system. A plus b equals 2, c equals negative 1, and 4a equals 4. So a must be 1, b must be 1, and c must be negative 1. Our partial fraction decomposition is this. Ta-da! Last case, I promise. Okay, the denominator has repeated irreducible quadratic factors. If it does, you kind of have to do it like the linear one, where if it's to the power of k, you do k minus whatever to get to the from 1, 2, 3, blah, 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 up to k. Ooh, that was a weird way of saying it, sorry. Okay, so the instructions here would be write the form of the partial fraction decomposition. All right, let's go. The denominator is already factored for us. We got a lot going on here though, okay? X is happening 3 times. That means one of our fractions needs to have the denominator of x. One of our fractions needs to have the denominator of x squared. Okay. And one of our fractions needs to have the denominator of x cubed. Okay. Then our next factor is an irreducible quadratic factor. So that needs to have the linear numerator of dx plus e, we just keep going with the letters, over x squared plus x plus 1. Plus, all right, we have another quadratic factor. Oh wait, this has multiplicity 3. So, a lot's going on. EF. So, fx plus g over this quadratic factor to the power of 1, then you'll have hx plus I over this quadratic factor to the power of 2. And your last one is jx plus k over this quadratic factor to the power of 3. OMG, how many of you want to solve this equation where you have 11 different variables? Thankfully, they just said write the form of the partial fraction decomposition, and we don't actually have to solve it. But remember when I said that the degree of p must be less than the degree of q? Well, if for some reason that doesn't happen, the way that you can still use partial fraction decomposition is if you use long division first. I'm going to show that right here, and not all the steps because you've done this before. Okay, x cubed times what gives me 2x to the 4th? Well, that would be 2x. 2x needs to go in the x column, so we'll put it right here. 2x, and then you're going to multiply everything in your divisor times 2x and put it below the dividend. Draw your line and change your signs to make it, oh, I did not change that sign. Minus minus is a positive, and we get 0, 0, 0, 5x plus 7. So this fraction can be rewritten as this. All right, and then the degree of the numerator now is less than the degree of the denominator, so you can decompose this. And oh wait, we actually did this in our first problem. We decomposed it right here. So your answer would be the following. Right here. Have a great day.